Hello, this is the chapter 4.1, and we will talk about vector spaces and subspaces. And we already investigate the ideas of the spaces and subspaces in the chapter 2, but we just touched it a little, look at the definition, try to figure out what can we do with spaces and subspaces. Finally, this is the time when we explore these ideas, because those ideas are indeed one of the most important in linear algebra and generally in mathematics. So what is a vector spaces? It's some kind of set of objects, and those objects can be matrices of vectors or can be any other mathematical objects which satisfy these 10 axioms of the vector spaces. For example, let's look at the interesting set which describes in a textbook. Let's look at the polynomials of degrees of n, and n is a positive number. And our variable t here can be any real numbers. Also, our coefficients from a0 to an can be also numbers, real or complex. So can this set of objects create a vector space? Let's just go through our axiom one by one and see if they are satisfied. For example, let's take the first property. We already have a polynomial p of t. Let's take another polynomial, call it q of t, and see if it will belong to a vector space. And it should be, because it has again power of n and this coefficients from b0 to bn. Okay, so let's check the first property. Let's add the p and q together and see if we will have an object which is also a n-degree polynomials. And indeed, by polynomial properties, we can come back the like term and get yet another polynomials with a real or complex coefficients. So it seems that the first property is satisfied. We can go to the second property, and that would be very similar proof, as well as the third one. Just the property polynomials will be sufficient. Property number 4 required a 0, and that's not easy to achieve. Any polynomial with one coefficient a0 equals 0 is the 0 polynomial. So the negative one, we can just take our coefficients and add the negative sign to them. That would work. So finally, this scalar multiplication. Again, we need to use a property of polynomials. Let's take our polynomial p of t and multiply it by some kind of scalar constant c. So what would we be? Because we are multiplying our polynomial by constant, we can distribute our c and basically increase each of our coefficient by c, which give us yet another polynomials. And we can similarly tackle the rest of the axioms, and we can show that indeed this polynomial form a vector space. So basically, we can put a bunch of objects in this vector space, and we can multiply them by constant, add them together, and that's great. But sometimes we don't need all the vector space. They actually can be humongous. Sometimes we want to restrict ourselves and use only the part of our vector space. And we will call this kind of like contained parts of the vector space a subspace. And because every element of our subspace, we call it H, would be also the member of vector space, we don't need all 10 axioms here. 3 actually should be enough. So we say that every subspace, if it's a subspace, should have a 0 vector. Also, our elements in the subspace should be what called closed under addition. So if we take any element of subspace, add them together, they should be also element of subspace. Finally, it also should be closed under multiplication. So we take any element of the subspace multiplied by a constant, and it also should belong in subspace. And let's look at the example of our polynomial in question 1. What if we take this polynomial and separate them into the subclass of the polynomials, which now can have only real coefficient a0, an, all the way to an? Because before they can be a real or complex, but now we basically separate them into the complex and real. Can this set of polynomials form a subspace? Let's just check our properties from A to C. First, the 0, the polynomial is equal 0, of course, will be included in our subspace because 0 is a real number. And any polynomials with one coefficient a0 is equal 0 should be included in our subspace. Second, again, if we have two polynomials p and q with real coefficient, then when we add them together by property of polynomials, all our coefficients will be added together, and since both of them are real numbers, the resulting polynomials will also have a real coefficient. So its set will be closed under addition. Finally, we can take our polynomial multiplied by the constant c, and again, we just multiply each of the coefficient by the real number c, which will give us again the real coefficient polynomial. So indeed, all of these three properties are valid, and our subset of polynomials form an actually subset. Okay, you probably noticed that there is a lot of multiplying by the constant and addition. So you probably already intuit that the linear combinations should be involved. And indeed, we can take a set of any vectors, like say from v1 to vn, and their linear set of all of the linear combinations will actually form as subspace. So yeah, it's really easy to make a subspace. Take few vectors, span them, and that will be a subspace. How do we know that the vector belong to a span space? No, it just has to be a solution. It should be a linear combination of our vector, just by definition of the span of the vectors. For example, let's look at 3 vector v1, v2, the 3, and here I give you actual real numbers. So, and let's take another vector y, which has a parameter h involved. So, if there is any value of parameter h, which make vector y a subset of the spanned subspace spanned by vector v1, v2, and v3. Okay, let's try to think about it. We know that the span is the linear combination. So if our vector y is in the subspace, then it should be expressed as a linear combination of vectors v1, v2, v3 with some kind of weights x1, x2, and x3. Okay, let's write down explicitly our vector v1, v2, and v3 and form a system of linear equations. So basically, if this system is consistent, then y belong our subspace. Or in other words, if there is any value of h which makes this system consistent, the y belong to a subspace. And the easiest way to figure out if our system consistent or not, of course, is write augmented matrix and reduce it to the echelon form. Let's reduce the first column to the echelon form, the second column, and that actually looks pretty good. We know that our only obstacle here is when our last line will have non-zero entry. So we need a value of h such that it gives us a row of zeros. Or in other words, our last entry of the third column, h minus 5, should be equal 0. In other words, h is equal 5 will give us a consistent systems, And consistent system means that our vector y should be expressed as a linear combination of vectors v, or in other words, y belong to a span subspace by vectors v. Okay, now go back to the chapter 4.1 and try to practice with a few more vector. Try to practice to apply the definition of space in this subspace, and just make yourself familiar with these very big ideas. We will come back to them many times within upcoming weeks.